hello everyone. We are going to discuss a very good problem today, which is given in NCERT miscellaneous exercise of set theory chapter, which is chapter first. And this question is question number 8 of miscellaneous exercise. So in this question, it's being asked that if uh, if A and B are two sets which are given to you, then we need to prove that A equals to A intersection B union A minus B, and A union B minus A equals to A union B. So these are two things which we need to prove. So before proving this, we will first dive into what exactly these entities mean, right? So we will see pictorially whether these things are making sense or not. So what we'll do is first let's try to see it in picture format. So let me take a universal set. So let me take a universal set like this, and within this let me take a set A, which is like this, and then I'll take another set which is B, which is like this. Alright. Now what I'll do is I will write like A here, B here. So and U over here. We know that A intersection B is this part, right? And we also know that this part is called A minus B, and this part is called B minus A. So what is A minus B? Whatever is available in A but not in B. So this part, right, from here. And similarly, if you look at B minus A, this is the part wherein whatever is available in B but not in A, right? So if you look at this entity, which is A intersection B union A minus B, which is nothing but this part and this part, which is nothing but A. So pictorially we can see that this is true. If this being a case 1, wherein there are some entities which are common to A and B both. Similarly for this part, A union B minus A union B minus A. So B minus A is this part, and A is whole of this part, whole of this is A. When you union A with B minus A, this is nothing but again A union B. So this is the entire thing from here to here, right? So the entire part will be A union B. So in case 1, we can see that this is true. Let's take another case wherein I take this as universal set again, and let me make it two sets which are disjoint. So A and B are having nothing in common. Let's say this is what we have over here. Now I have A like this, B like this, U like this. So when I look at here, we'll find A intersection B is 5 because there is nothing common. So when I look at this entity, A minus B, what will happen to A minus B? A minus B will be nothing but A itself because there is nothing common between A and B. Similarly, B minus A will be nothing but B because there is nothing common between B and A. So A intersection B union A minus B, this entity if you look at, this will be nothing but 5 union A, which is nothing but A. Similarly, when I look at this entity, which is A union B minus A, which is nothing but A union B itself, right? So I can say that because B minus A equals to B. So this is case 2 when there are nothing in common, right? Let's take another case when there is, let's assume that now A becomes a subset of B. So now let's look at this case as well, wherein this one is bigger, and I take another one within this, right? So now let me write it. So this is my U, this is my A is a superset and B is my subset, right? When I look at this part, again A intersection B, when I look at A intersection B, whatever is available in A and B both, it's nothing but B itself. And when I look at A minus B, whatever is available in B but not in, whatever is available in A but not in B, which is nothing but this part, the ring part, right? So when I do a union of A minus B with a B, I can say that I can get another, basically A itself. So in this case also, A intersection B union A minus B will be nothing but your A itself. When I look at B minus A, whatever is available in B but not in A, there is nothing like that, that's why it's a phi. So when you do basically when you look at the second entity, which is A union B minus A, when I do A with A B minus A, so it will be A itself. So let me write it down. So A union B minus A, right? Which will be nothing but A itself, because B minus A is phi. When I do A union B itself, what will happen here? A and since B is common to A and B both, this will be nothing but A itself. So in this case also, we can prove that this part is equal to this part, right? Similarly, in the fourth example, when what I can do is I can reverse it. I can say my A is smaller and basically B is bigger, as in A is my superset and B is my subset, right? So what I can do is, right, now I call my B this one and A this one, right? Look at here, A intersection B. What will be A intersection B? Will be nothing but A itself. When I look at A minus B, whatever is available in B but not in A, nothing there. So when I do a union of these two, I will get A. Similarly, if I look at B minus A, what will be B minus A? So B minus A would be whatever is available in B but not in A. So this part, right? And then the last bit, which is nothing but A. So when I do A union with this part itself, I'll get nothing but A union B. So what I am seeing over here is that whatever be the case, this is true, right? So now I have seen that in all the cases it's true. We just wanted to see it pictorially. Now let's try to prove it. Let's try to prove this part, which is on the right side, and see how it comes out. So let's take the LHS of second part. So LHS of second part is A union B minus A. What we'll do over here is we'll use our commutative law and make it B minus A union, or just keep it like that. So we can as well write A union B minus A as B intersection A dash. When we write that, we can as well write that A union B intersection A union A dash using our distributive law. Alright. Now A union B is A union B, but when we look at this A, this part, this becomes universal set U, and doing an intersection of anything with a universal set will return the same set. So this is A union B. Alright, which is nothing but the RHS we need to prove, which is proved. Alright, this part is done. Let's do another thing, which is a similar way. Can we prove as well that B union A minus B is also A union B? Let's see. So let's take another LHS over here, which is nothing but B union A minus B, and we write that again B union A intersection B dash. Now mark it over here, it's B dash, over here it was A dash, because whatever is in minus A would come over here, right? So now you can see this can be written as B union A, and again an intersection B union B dash, again using distributive law over here, distributive law. B union A can be written as A union B using commutative law, and this part becomes U, commutative law. Now A union B intersection, you will again return A union B. Alright, so we can see that this part is also equal to A union B. Now let's try to see this part. We'll take the right hand side of it, RHS of it. So A intersection B and then union of A minus B. Let's move a little further. So what this will become is, we'll write again A minus B union A intersection B. Again, using our commutative law, we can write that. Now write using our distributive law, write A minus B union A and then intersection A minus B union B. A minus B union A. So anything, if you do a union of A minus B with U, it will return you an A. Whereas A minus B intersection A minus B union B would return you A union B. And again A intersection A union B will return you set A. So let's try to see these two parts if you have not understood. So when you look at the Venn diagram of this, say this is your A, this is your B, right? This is your A, this is your B, this is your U. So this part would represent A intersection B, as we have seen. This part would represent your A minus B, right? So look at A minus B and union A. When this part is A minus B, this part is A. Can you do a union of anything with a union with the same set, right? This set will return in the same set. A has been returned. This part we have already proved above. So this is why A intersection A union B. Now look at A intersection A union B. A is this whole thing. A union B is the whole thing. When you do A intersection A union B, you will be getting A. So this is nothing but LHS which we had to prove. So yes. So this second, this is one way of doing it. Now what we will do over here is, what we try to do in this case is, we try to show one set as the subset of another set of subset of first one. And when we do it this way, then we prove that one set is equal to another one. So what I mean is, when we prove that A is a subset of B and a B is a subset of A, this implies A equals to B. This is what we will try to do over here. So I'm just erasing it because this is something. Oh, okay. Now this one, this part. So I'll just remove this part and I'll start the process of proof. Alright. So what we do is, we start with, let X is an element of A. Alright. When X is an element of, we cannot say that X is an element of A intersection B, because it may be an element, may not be. Alright. So there arises two cases. Case one would be X is an element of A intersection B. This is first case. And case two would be actually X is not an element of A intersection B. So we'll try to solve this case one by one. So we are going to solve this case one. So when X is an element of A intersection B, this implies X is an element of A and X is an element of B as well, right? Which is okay. And when X is an element of A intersection B, we can just say that X is an element of A intersection B union anything, A minus B, anything. It could be anything. It could be phi, it could be universal set or anything. But since X is an element of A intersection B, it will be an element of this as well. So this implies, we started with X is an element of A and we came to this. This implies A is a subset of A intersection B union A minus B. Alright, this is my case 1. Now let's take what is case 2. So case 2, it says X is not an element of A intersection B. Alright. When this is the case, we know that as X is an element of A, this means X is not an element of E because X is not an element of A intersection B. This implies X is an element of A minus B. This implies again X is an element of A minus B union A intersection B. So what I mean is that if X is an element of this, then it could be an element of this union anything. It could be anything. It could be a U, it could be a phi, anything, right? But since X is an element of A minus B, it could be an element of this as well. So here again, as we prove, A is a subset of A intersection B union A minus B. All right. So let's say this is 1, this is 2. In both the cases, we can see that from 1 and 2, we can see that A is a subset of A intersection B union A minus B. This is something which we have understood. Call it expression theory. Alright. Now let's move further. Now what we have to do, we have to prove it other way around. So what we will do is we will prove this. We will say that let Y is an element of A intersection B union A minus B. This implies Y is an element of A intersection B or Y is an element of A minus B. This implies Y is an element of A or, oh sorry, not or, but rather it is an and Y is an element of B. Okay, so what we have written, Y is an element of A and Y is an element of B, or Y is an element of A and Y is not an element of B. A minus B implies this. In both the cases, we can say that Y is an element of A at least. This one we can be at least sure of, right? So this implies we can say that A intersection B union A minus B is a subset of A. So this is my equation 4. From 3 and 4, we can say that A equals to A intersection B union A minus B. Alright, so this is proved.